next project is a joint project between Mohammed Haj and Ishwar Puri. They are unavailable today, so Shobhak Paul is going to present for them. They were Ishwar's graduate student.
Good morning, everyone. So I'll be presenting this work on behalf of Professor Haj and Professor Puri. So this work is based on modeling the space heating applications based on adsorption and desorption of moisture in porous materials. So it's thermal energy storage in porous materials with adsorption and desorption of moisture. What is the key research question here? So how can we efficiently store solar energy in summer, hope to store it across seasons, and use that stored energy in winter for space heating applications? So existing methods of doing that in form of sensible and latent heat are not very good because they suffer from severe heat losses. So one way to circumvent that issue is using adsorption-desorption based cycles where in winter, we pass moisture through the porous materials that releases the heat of adsorption and heats up the material, and that heat can be used for space heating applications. And in summer, we expose that same material to sun, where upon receiving the heat from sun, the material gets dissolved, releases the moisture, and it's recharged. So it completes this cycle. But there is a wide variety of choice of adsorbent-adsorbent material pair, which makes the design of such processes non-trivial. So our objective was to develop a fundamental model which helps us understanding what goes on, as well as to help us facilitate design and optimize the process. But the existing techniques to characterize flow through porous media using Navier-Stokes equation suffer from a few disadvantages. One is that we don't know the exact pore network ahead of time. We can only comment on whether it's microporous or nanoporous based on experimental observations, but the exact pore network information cannot be derived. So that prevents us from using exact Navier-Stokes equations. Also, methods based on Darcy's law, which is an empirical law, it's not accurate because it involves a lot of empirical constants. Our approach was much more fundamental. We used species transport equation to model the transport of moisture through the porous material. So the process has two major components. One is the kinetics part, which involves the adsorption and desorption of moisture, and which tracks the evolution, the spatial and temporal evolution of the variable C, which is the moisture concentration. And another part is thermal transport, which influences the temperature inside this porous solid. But these two processes are interrelated. As the moisture gets adsorbed, it releases heat of adsorption, and that affects temperature. As temperature gets affected, that in turn affects the rate of adsorption and desorption. So this is a coupled process. So our model is actually capable of tracking that coupling, and it simulates an open flow process where we pass humid air through a porous solid and release the heat. So it can simulate any open flow adsorption-desorption process. So it's flexible enough to incorporate in range of materials, adsorption-adsorbent pair, so that's according to that fits into our objective. And since it's a transient model, we can track what happens from, say, t is equal to 0 till a steady state is reached. So it's a simple and accurate tool. It's not empirical, and we can use it for design thermal storage applications. These are some of the results based on a similar experiment. So our first goal was to validate our model with an existing experiment, whether the results from our predictions make much sense or not. So this is a similar experiment performed earlier by a group in Canada, University of Ottawa, I believe. So what you see here is the moisture concentrated. So it's a specific mixing ratio, the amount of moisture, kg of H2O per kg of dry air at the outlet of the porous solid as the air flows through it. So initially there will be no moisture present at the outlet because all the moisture is getting absorbed in the porous solid. And the dash dot line here is the inlet moisture concentration, which is kept constant, but the outlet moisture concentration is zero at the for some initial period of time. But with time, the porous solid starts to get saturated, and at steady state, it's completely saturated, so there is no more adsorption present here. So inlet moisture concentration and outlet moisture concentration is exactly equal. So whatever moisture comes in through the air stream gets out exactly. So at that phase, we call that the material has been, the porous solid has been completely exhausted and there is no more adsorption. So during this adsorption, heat is released. As a result, temperature increases. So we can see most of the adsorption takes place within the first 40% of the entire interval of time, which may not be so basically here 1 stands for 120 minutes. So this experiment was carried out for a span of 2 hours, and all the heat is released within 40% of that interval. So in first a few 20 or 30 minutes or so, which is not an ideal scenario if you consider heating application, space heating application. But then this is the model gives us a way to play around with the shape of this curve, the temperature rise at the outlet. We can play around with the input parameters which affect this process, and so basically that gives us a way to optimize and design different applications. And another important observation is the fact that the inlet air temperature during desorption plays a role in optimizing cost in the process, which we get from our model. So given a certain interval of time in the beginning of desorption process, you can look at the material and say, what is the percentage of regeneration, which is here on this axis. So if it's completely regenerated after that interval, that means it's completely, we have completely desorbed all the moisture in the material, then it's 100% regenerated. But if we use, so beyond a certain temperature, which is like 250 degrees Celsius or so, beyond a certain inlet air temperature, there is no additional advantage of using a higher temperature to desorb the material. So if we use a lower temperature, then after a certain interval of time, the material is only partially regenerated. So what this plot tells us is that if we want a quicker regeneration, we have to use a higher inlet temperature, which incurs additional cost. So we have to optimize the time for regenerating for a solid and amount of energy we can use to do that. So still in the early stage, we were using our model to identify existing materials with highest energy storage density, and using uncertainty analysis, we're trying to identify which of the input conditions has strongest influence on the process. Also, down the line, we'll also look at, from the material science perspective, look at materials which will give us even more higher energy storage density, and we can sort of develop novel materials with prescribed values of that. So in summary, we have developed an efficient design tool which can describe adsorption and desorption based thermal energy storage, seeking joint funding with SAIC. And whatever results has been obtained so far, we're considering communicate in International Journal of Heat and Mass Transfer. The manuscript is under preparation. And in fact, if you look at the model, it's so general because it can track any fundamental, any adsorption-desorption based heat release and absorption process. So it can also simulate similar, like for example, solar air conditioning or CO2 separation, which also involves similar processes. So our model can also be used for those purposes. We thank our key collaborator, Bill Wong in SIC, for his valuable inputs and suggestions. Thank you all.